Hey everyone, welcome back to AP Precalc. This is lesson 1.13. Let's get right into it. All right, so here's the bell ringer for today. Pause the video now if you haven't done this already, because I am about to go over the answer. All right, so here we want to figure out what point is 5 comma 4 mapped to on the transformation y equals negative 2 g x plus 3 plus 1. And so the first thing we want to ask ourselves is what is happening to our x and our y value. And so first off, we see x plus 3, which is moving it. Remember, anything inside the parentheses is going to be the inverse. So this is moving it left 3. And now let's take a look at what's happening to our y value. We have minus 2 multiplied on the outside. So this is taking our y value and multiplying it by negative 2. And then this plus 1 is moving the graph up 1 after as a result. So let's take a look at what we need to do here. For our x value, the only thing affecting our x value is that x plus 3, in which case we're moving it left 3, which means 5 minus 3 should be 2, should be our x value of our new coordinate. And then our y coordinate, this is 4, and we need to now multiply it by negative 2 to get negative 8. And then if we add 1, we should get negative 7 as our result. So A should be our correct answer there. Now, what will you need to know after today's lesson? You will need to know how to graph an equation in Desmos, how to find the zeros of any equation in Desmos, how to find local maxes and mins, and also an intersection point between two graphs or lines in Desmos as well. And I'm going to go over all of that today with tons of examples. Now, why am I teaching you how to use Desmos versus like a TI-84? Desmos is way better overall. You won't have to worry about memorizing keystrokes in Desmos. A lot of it just comes naturally. In addition, you will never see a calculator error if you use Desmos correctly, whereas there's lots of little things in the TI-84 that causes calculator errors, such as subtracting a negative number and different things like that. The interface it's just so much easier to use Desmos than the TI-84, and just a lot smoother and better of a process overall. So first off, make sure you are using the right version. And so what I would recommend is go to Google and search Desmos AP version. Here, you should then be on a website that has a green bar. This is because if you just go to the main Desmos website, they have a little bit more functionality than what will be seen on your AP exam. So how it's going to work is on your AP exam, when you get to a graphing calculator question or the graphing calculator portion, you will have the option to enlarge a window that has Desmos, and you can use Desmos for any given question. That's going to be super helpful, and this is the version that they will give you. This is also the version that's on the SAT as well, so very useful to get familiar with this version versus the other version that they have that has a little bit more functionality. Now, first off, we will be learning how to find zeros. So pretty much type in your equation in Desmos, and then hover your mouse over any time you see a zero, and the point should pop up. It should appear gray. And so let's try example 1. I will walk you through it. So the way this video lesson will work is I have screen recorded me solving each problem, so I'm just going to play those videos back. All right, so for example 1, we are going to want to find the zeros of y equals 2x squared minus 7.2x minus 6. Once we have that, we can see that line here, and you want to just click on those zeros. Remember, zeros are where it touches the x-axis, and that should be our two zeros there. So negative 0.698 and 4.298 should be our answer there. All right, now example 2, approximate the real zeros of that equation as decimal approximations. So for example 2, we want to approximate the real zeros of f of x equals x to the fourth minus x squared minus x minus 2 as decimal approximation. So here it is important to know that decimal approximations means 3 decimal places, and so we are going to want to round our answers to 3 decimal places. I found the 2 zeros here, which is where it crosses the x-axis. However, our answer should be negative 1.229 and 1.566. All right, if you round to fewer decimal places, it would be marked wrong on an AP exam, so just be cognizant of that. All right, for example 3, we want to find the intersection points of f of x equals 2x squared minus 7.2x minus 6, and of the line g of x equals 2x minus 1. Once we have it, we can see two intersection points right here and right here. So when you hover over there, there we go. And these should be our answers. However, remember, we want decimal approximations, so kind of round to 3 decimal places. So 5.091, comma 9.182, and negative 0.491, comma negative 1.982 should be our answers there. All right, so for example 4, we want to find the intersection points between f of x equals 5x minus 1 and g of x equals x to the 4th, minus x cubed plus 2x minus 9. So here we just want to hover over our points like so. And then our 2 points here should be 2.268, comma 10.342, rounding to 3 decimal places, and negative 1.241, comma negative 7.203, and that should be our answer. All right, so when we want to find when an equation equals or is the same as a certain value, we want to do two things. The first thing we want to do is graph the equation. So for example 5, when g of x equals 3x squared minus 5x plus 7, and then we want to see where is g of x equal to 6, we are going to just graph another line, g of x equals to 6, and then find the x coordinates of our intersection points. So our two x coordinates here should be 0.232 and 1.434, and those two x values should be our answer there. So for example 6, we want to find our local maximum and minimum of f of x equals 2x cubed minus 2x squared minus 7.2x minus 6. And so here we kind of need to move the graph around, so we'll just scroll down a little bit, and then we can find a local maximum if you just hover over that, and a local minimum here, hovering over those 2 points. So we should have a local maximum at negative 0.812, comma negative 2.543, and a local minimum at 1.478, comma negative 14.553, and that should be our two local extrema, one being our local max and the other being our local min. All right, so for example 7, which is on the next page, we want to find the relative minimums and relative maximums of f of x equals x cubed minus 2x squared plus 4. There we go. And so here we should find a relative maximum, that peak at 0, 4, and a relative minimum right here at 1.333, 2.815. And so those 2 points should be our relative minimum and our relative maximum, with 0.4 being our maximum, obviously, and then 1.3, 2.8 being our relative minimum. All right, so the next thing that we're going to talk about is selecting an appropriate model type. And so sometimes you may be given the context of a story problem or situation and may be asked to identify whether it's linear, quadratic, or cubic. Linear will roughly be constant rates of change, meaning the graph should look like a straight line. So as something increases, the y variable should either increase like this, or the y variable should decrease. So it should be either just straightly going up or going down. Quadratic models will be roughly linear rates of change, or basically just curves with a single minimum, like so, or a single maximum, or any story problem that involves area. So that's the key thing, right? Remember, area, the square units, it's going to be units squared, and so that is similar or indicative of a quadratic model. And then cubic models will involve volume. So remember, cubic, if you're trying to figure out volume, it's going to be some units cubed. And so this is going to be indicative of a cubic model here. So let's try with 3 real quick examples. Example 8, for each of the following situations, determine whether a linear, quadratic, or cubic model would be most appropriate. So the first one here, balloons are filled in with water for a epic water balloon fight. Each water balloon is roughly spherical. The radius is measured relative to the amount of water it holds. So we're looking at the radius relative to the amount of water it holds. This is another fancy way of saying the volume of the water balloon. So we're looking at the radius to the volume, which this is going to be talking about volume. So this is going to be a cubic equation, or a cubic model would be most appropriate. For B, pizzas are on sale at the grocery store. We are looking at the total number of pizzas relative to the total price of the purchase. So here, obviously, right, the more pizzas we buy, the bigger our purchase is going to get. And so this is probably going to be linear, right? It's just always increasing in this case. And so linear would be the best model for 8B. 8C, sprinklers placed on a yard to water the grass, rotates in a circular pattern. The radius is measured relative to the area watered by the sprinkler. So remember, the area is going to talk about any quadratic model, right? Because area for at least a circle equals pi r squared. And so here we are probably going to lean towards quadratic as the best model for 8C. All right, example number 9 and 10 we can knock out in the same video. Just be cognizant of making sure you're zooming all the way out before you give your answers. So for example 9 and 10, we're dealing with the same equation, so we really only need to graph it once. For example 9, we want to see where is g of x, which is equal to negative 0.17x cubed plus 2x squared, minus 1.24. Where is this equal to g of x equals 1? Like that. And now the mistake that a lot of students may make is they may only find these two values and assume that they're done. However, this looks like a quadratic function, and looking at our equation, I know it has to be cubic. So where's the rest of this graph? And this is why it's really important sometimes to zoom out and make sure you have the whole picture, because here we are missing one more time where it equals 1, which is right here at 11.668, and so our 3 points should be negative 1.015, 1.112, and 11.668 should be our 3 x values that make g of x equal to 1. Now for example 10, we can knock this out in the same time. This is the same equation, so we already have it graphed, and we want to figure out the x values of any local extrema. So here we want to find a local minimum, which is right there. And then we can also find a local maximum, which you might have to go up a little bit, but it should be right here. And so if you weren't zoomed out, you would only see that local minimum. You would be kind of missing that local max. And so our local min should be 0, negative 1.24, and our local maximum should be 7.843, 39.770, rounding to 3 decimal places there. All right, and now the final thing that we're going to be talking about is domain and range. So you may be asked about the domain and range of story problems in context of specific situations. So think about how the domain or how the range, or more importantly, how your x or y values really are restricted in terms of story problems, right? If it's just an equation, domain and range are much different, right? Our domain was like all real numbers except x equals, this number, and this number when we were talking about rational functions. But with story problems, it gets a little bit more specific because we want our x and our y values to make sense. So let's work through example 11. Here we have a figure shows the height of a ball, which the y value is feet, in feet of the height when it is tossed off a roof over x seconds. So our x variable is seconds here. This is modeled by this equation. Using the graph and the story context provided, explain how the domain values of the function should be limited by the context of the problem. So based on the context of this problem, right, the domain of f consists of non-negative values. What this means is we want to kind of exclude any point where t is less than 0, right? Because it doesn't make sense. You can't have negative time. And that's the biggest thing to remember is you cannot have a negative time value. So here, this is good. We address that you can't have a negative time value. We also know that you cannot have a negative y value. So because the ball cannot go to a negative height, the furthest or the most amount of time that we can actually capture is when it hits the ground, which is at 11 seconds. So we can kind of go only from 0 to 11 because of that range restriction there. And so that is going to be our proposed domain. 0 is less than or equal to x, which is less than or equal to 11 seconds there. So talking about both of those should get you full points on an AP exam for example 11. And finally, example 12, same situation, but this time we want to explain how the range values should be limited by the context of this problem. So what we would want to say here is the ball cannot have a negative height. And then we also want to address how, because this is a quadratic function that is concave down, there is going to be a maximum at 4,98. And you would know this because this would be an equation that you would be given Desmos for and be able to find that maximum that you just found. So the ball cannot have a negative height. So the lowest height possible is 0 feet, and because we'll say f of x is a concave down quadratic, there is a maximum at 4,98, making our range, which remember range is talking about our y values, from 0 to y to 98. Or you could put here, if you wanted to replace that with 0 f of x, 98, that's fine too. And that should get you full points if the AP exam was asking about range. So this is a common question where they would give you a story context, they would give you Desmos, they would give you that graphing calculator, but then ask you about domain and range. And so you should expect to see one of these on your next test for sure.